I've been playing with these balances for about 5 days now, and I keep finding new things to do with them. I've had a lot of ideas for investigations and little experiments we can do with them to measure all sorts of different interesting physical quantities. I did think about turning this into another 2 or 3 videos, but I thought probably best to keep it to one. In order for this to just fit in one video, I did have to decide what I was going to talk about. I've decided on 3 main concepts. The first is simple harmonic motion. I also want to touch on resonance. And then I want to talk about how this system loses energy over time. Simple harmonic motion is a type of periodic motion that appears all over different parts of physics. The requirement for simple harmonic motion to occur is simply that the restoring force is proportional to the displacement of the object. We can think of the restoring force as whatever force is pushing our object back towards its equilibrium position. In the case of a mass oscillating on a spring, the restoring force is the springiness of that spring, what we call the spring constant, multiplied by the displacement from equilibrium position. This assumption that the restoring force is proportional to the displacement of the object is true for our inertial balance as long as our initial displacement is not too high. I'm a big fan of the equations of physics and I love derivations, but unfortunately this one requires a little bit of a deeper knowledge of parts of calculus, specifically ordinary differential equations. Let's have a quick look at what it looks like, but I'm not going to go into too much detail on how we get from one step to the next. Let's start from this assumption that the restoring force is proportional to the displacement from the equilibrium position. In this case, we can write our restoring force as F equals Kx. K is just some constant associated with the springiness of my inertial balance. We can combine this with Newton's second law, F equals ma. We can set them equal to each other because these two forces should be the same. We're going to take Newton's original definition of this law and say that the acceleration of this object is going to be the second derivative of the object's position with respect to time. We write that as d squared x dt squared. We're then going to use a substitution and we're going to introduce a Greek letter omega. Omega is a symbol that comes up all over physics, especially when we have some sort of oscillation or rotation. Here we're going to say omega squared equals k divided by m. When we make this substitution, we get what's called an ordinary differential equation, d squared x dt squared plus omega squared x equals 0. There are actually many possible solutions to this equation, but we're going to take the general case. When you solve this, you get an equation that looks like this. X equals a cos omega t plus phi, where x is the displacement of the object, a is the amplitude of oscillation, omega is the rotational frequency of the object, t is the time, phi is a constant that gives the phase of this oscillation. This gives us a couple of key relationships for free. The relationship between frequency and rotational frequency, f equals omega on 2 pi, which tells us that the period of the oscillation here is going to be 2 pi on omega. This also gives us an expression for period in terms of mass. Period is going to be equal to 2 pi multiplied by the square root of m divided by k. This formula is actually at the heart of how we use the inertial balance to actually measure the mass of objects. So let's not get lost in the weeds here. What does this tell us? This says that if I record the motion of my inertial balance, I should expect to see a cos curve or some other sinusoidal curve in its oscillation. And the question becomes, why is this relevant? It turns out simple harmonic motion is pretty much the simplest form of periodic motion. It's a type of oscillation or movement or rotation that is very predictable and relies on simple rules. By closely investigating a simple system, we can get a good intuitive understanding for how this type of motion works. Something else to notice is that we haven't made any extra assumptions in deriving this equation other than our restoring force being proportional to our displacement. In order to fully describe a simple system undergoing simple harmonic motion, all we need to know is the amplitude of its motion, its rotational frequency, and its phase. A little later on in the video, we'll look at how we might use a simple model like this and then extend it with some more complex analysis in order to get a more full picture of our real world. When we look at this balance vibrating, what does it bring to mind? Recently in my year 11 physics class, we've been talking about standing waves and resonance. So immediately, as soon as I started seeing this thing vibrating, my brain lit up and said, this is an example of resonance. We should see as the inertial balance vibrates, effectively what we've got here is a string open at one end. The end of the balance that does not move is a node. It doesn't oscillate whatsoever. but the other end that is free to move oscillates between its maximum and minimum displacement. This is an antinode. What we should notice is that the inertial balance is vibrating at its fundamental frequency. The fundamental frequency of an object is the lowest natural frequency at which it will vibrate. In this case, what that means is this is the lowest frequency vibration that has a node at one end of the inertial balance and an antinode at the other end of the inertial balance. Resonance is another one of these phenomena that pops up everywhere in physics. It comes up in electronics, it comes up in music, it comes up obviously in motion, and it also comes up in the structure of atoms. In almost all places where you have vibration occurring, resonance is also found. When things vibrate naturally, we can generally assume that they are at resonance. In our case, the resonant frequency of this balance is going to depend on its physical properties. Things like the stiffness of the saw blades, the length of the saw blades, the mass of the wooden block, and the distance between the saw blades when they vibrate. Resonance here is not just a coincidence. Without resonance occurring, we would not be able to use this inertial balance to measure the mass of objects that are placed on it. If we control the other properties of this balance, for example, the length of the arms, the springiness, and all those sorts of things, by keeping the balance the same and just change the mass, we can look at the relationship then between the frequency of oscillation and the mass placed on the balance. Energy is being lost constantly by this balance as it oscillates back and forth. Some of this is lost as heat energy as the end of the balance runs into air particles on its way past and gives them some of its kinetic energy. We also lose heat energy to the particles of the metal that makes up the saw blades as they rub past one another. Something else that contributes to energy loss in this system is the fact that I have two saw arms on this balance. Each arm is going to have a slightly different natural frequency simply because of my inaccuracies in putting this apparatus together. Because each has a slightly different natural frequency, they want to vibrate at slightly different frequencies, which means neither of them gets to spend their whole time right at that fundamental frequency. Resonance is the place where you have maximum energy transfer and where the amplitude of your vibration is going to be at a maximum too. This means any time that the saw blades spend not vibrating at their resonant frequency, they are going to be losing energy. One of the most intriguing elements of playing with this apparatus was the way that the energy loss differed between the single-armed balance and the two-armed balance. The single-arm balance lost energy so much more slowly than the two-armed balance. And at first I couldn't work out why this was. There are really two things going on here. One is the fact that with just a single arm, that arm is allowed to vibrate at its resonant frequency without interference. Whereas with the two blades, because they have slightly different natural frequencies, they won't be oscillating at that natural frequency for the entire time. The other factor that comes into play is damping. The saw blades aren't able to bend exactly how they want. They want to flex in the same direction all the way along, but that's not possible with the two blades. The way that they are screwed to the block means that their oscillation is damped or reduced by that block over time. Let's draw all of this together and see if we can figure out the equations that govern how these inertial balances work. First, let's take a look at what it looks like when this two-arm balance oscillates back and forth over time. Here's a graph I made that shows how it moves from left to right as we let it oscillate. What we'll notice is that parts of this look a lot like a cos or a sine curve. They are sinusoidal. What we can see though is the amplitude of this oscillation is decreasing over time, but the frequency is remaining the same. The first step here is to figure out the wave that represents the oscillation of this balance. It turns out it's this cos curve. We can see when I put the cos curve over the top of the motion of the balance, they fit perfectly, but the amplitude of the cos curve remains the same over time. So we need an extra piece of information here to figure out how these oscillations are decreasing over time. I was able to find the equation of the curve that shows how this decreases over time. Here's what it looks like overlaid on the oscillation of the actual balance. So here we've taken our definition of simple harmonic motion to identify that there must be a cos or a sine curve that describes the motion of this balance over time. But I also know that this system is losing energy, and so I need to introduce an extra term into my equation to show how that happens. And that term is an exponential in terms of negative t. When I multiply the exponential and the sine curve together, what I get perfectly matches my observations. I really like this because it gives us a hint into how physicists actually do their work. Physicists aren't given the laws of nature. They're not given formulas written down for them. Physicists do experiments to determine the mathematical laws that underpin physical interactions. What we've done here is taken a mathematical law that we know and then extended it so it works more fully in the real world. Take note that this is still not a complete description of the movement of the balance. Another thing that I like about this experiment is it shows that things are not the same at all scales. A small change, like going from one arm to two arms, can drastically change the behavior of a system. If we look at how the motion of the one-armed balance changes over time, you can see it also decreases. But if I try and use the same rules to show how this changes, it doesn't fit. If I lay the two curves on top of each other, you can see that the single-armed balance stays oscillating for much longer. It turns out that the extra term I have to introduce here is not an exponential in terms of t. It's an exponential in terms of the square root of t, which means that it slows down and gets towards that x-axis much more slowly. So we have now two equations that describe the motion of the two-armed balance and the motion of the one-armed balance. Ideally, we can link our mathematical understanding and our physical intuition for these scenarios really well. We can see the difference in the exponential term of these functions as a description of how the system loses energy over time. This is really my favorite part about teaching physics, is the idea that you can get all this interesting information and generalizations about the universe from such a simple apparatus. It's literally just two blocks of wood and two saw blades screwed together. And there are all these insights that I can gain about the physical reality that we live in. I hope that watching me go through this process has inspired some of you to do some investigations of your own. If that's the case, I'd love to hear about it, so please do let me know. I think I'm gonna leave the inertial balance to one side for now and maybe pick up a different project. If you have any ideas or anything you'd like to see, please do let me know as well. And if you have any questions or feedback, please leave that in the comments below. Thank you so much for watching, and I will see you next time.